In this video, we're going to start looking at set theory, and we're going to start by defining what are sets, looking at some examples and looking at some properties of those sets. So what is a set? A set is an unordered collection of objects called elements. So a couple of things to note here. Objects called elements, they could be anything. They don't have to be what we traditionally think of mathematical objects like numbers. They can be anything. Two other important properties here. A set is unordered. That means order doesn't matter. Sets don't contain any information about order. The other thing is, if these are collections of objects, then an object can't appear twice in the same collection. So every element in a set would be unique. So look at some examples. So let A be the set of all countries in the United Kingdom. So what would be in this set? The objects that we are calling elements would be England, Northern Ireland, Scotland and Wales. Now, even though I've listed these in order here, again, order doesn't matter. I was just trying to show I'm not biased by being in alphabetical order. So there's two ways of writing out this set. So we can either write down a sentence which explains exactly what's in it, describes the things in it, and that's a completely valid way of defining a set. The other way is to list out all its elements. So here, convention says we separate the elements by commas, and we contain all those elements within curly brackets. Another convention, which is not always stuck to, but I'd like us to always stick to this, is that sets are usually named after capital letters. And then we can use small letters then to denote elements inside the set. Let's look at another example. Let B be the set of outcomes of rolling a six-sided die. Imagine we took that dice and we painted the 6 to be another 1. What would the set of outcomes then be? Well, it would be 1, 2, 3, 4, 5. We wouldn't put the second one in because there is no two ones. There's only one outcome 1. There's just two ways of getting to it. So again, sets have to contain unique elements. Another example. Here, let C be the set of positive even numbers. So again, we can list out the elements. C contains 2, 4, 6, 8, 10, and so on. Now, even though we've listed enough numbers there so we can guess what comes next, that listing out the numbers like that is not sufficient. And we can't list all these numbers, all the positive even numbers, because there's an infinite amount of them. But listing them like that is not sufficient to tell us exactly what is in this set. So here's an example of a set where we actually need to write down that descriptive sentence in order to really be able to actually define this set. Let's look at some language we use when we talk about sets. So let's think about that set A again, the set of all countries in the United Kingdom. Now Wales belongs to A, or Wales is an element of A. And we use this notation, this little funny E thing, to say that Wales is an element of A. That is not an E, that is a symbol all to itself, and the direction is important here. So Wales is an element of A is not an element of Wales. So make sure you get that direction of that symbol correct. Now, what if something's not an element of something? So Spain is not an element of A because Spain is not in the United Kingdom. And here we say is not an element of or does not belong to. And we use the same symbol with a slash through it, just like we would with a not equal sign. It was a not an element of sign. Spain is not an element of A. Similarly, Cardiff is not an element of A. And it might seem really intuitive to us to go, well, Cardiff's in Wales and Wales is in A, therefore Cardiff must be in A. But that's not true. And that's not true because of how we defined A. We defined A as the set of countries of the United Kingdom. Cardiff is not a country of the United Kingdom. even though it's inside Wales. So Cardiff is not an element of A. What other properties can we talk about with sets? So we can talk about the cardinality of a set, or sometimes we call it the size of a set. And what is that? The size or cardinality is the number of elements in a set. So again, A, the set of all countries in the United Kingdom. There are 4 elements in that set, so the cardinality of A is 4, or the size of A is 4. Think about set C we had earlier, the set of all positive even numbers. What's the cardinality of that set? Actually, there's an infinite amount of things in that set, so it starts to not make sense to talk about cardinality. But it does start making sense to be able to categorize sets, whether they are finite or infinite. So countable sets, I'll go into what countable is in a bit, but countable sets can either be finite or infinite, and we've already seen 2 examples of this. So the set of all countries in the UK is a finite set, its cardinality is a finite number. An infinite set would be, like we saw before, the set of all even numbers. There's an infinite amount of them. But both of these sets are countable. What do I mean by countable? Well, we can start listing off all the elements in these sets. So that's quite easy with a finitely countable set. So England, Northern Ireland, Scotland, Wales. With infinitely countable sets, we will be here forever counting them all, but we can still start listing them off. We can say 2, 4, 6, 8, and so on. They are countable. Now, given a precise definition of countable and uncountable is a bit beyond this course, but I want to be able to give you examples of uncountable sets, because they are very important, and then give you a feel for the difference between countable and countable. So uncountable sets actually come in 2 different types. They can be bounded or unbounded. So an example of a bounded uncountable set would be the set of all times in a day. Now the set of all times in a day is not just 1 o'clock, 2 o'clock, 3 o'clock, because we could have 1 minute past 1, 1 second past 1, or a nanosecond past 1, and we can keep going smaller and smaller and smaller. So there is an infinite amount of things in that set. It's uncountable because we can't start listing them off. What is the first element of that set? Well, let's just say 1 o'clock. What is the second element of that set? That doesn't make sense. Is it 1 o'clock plus a nanosecond? 1 o'clock plus half a nanosecond? 1 o'clock plus a tenth of a nanosecond? We can't start listing them off. Even if we could start listing them off, we could be here forever before we ever reach 2 o'clock. In fact, we could be here forever before we ever reach 1 minute past 1. In uncountably countable sets, we tend to think of them as between any 2 elements, there's an infinite amount of other elements. But this set is bounded. Why is it bounded? Because it does have a maximum and a minimum. So there's a start of a day and an end of a day. You can't have a time of the day which is before the start of the day, midnight, and you can't have a time of day which is after the end of the day, the next midnight. And then quite naturally then, unbounded uncountable sets would be, so the set of all real numbers. Again, you can't just list all these numbers off like we could with the even numbers, but these are unbounded because it doesn't have a maximum or minimum. The maximum, these sets go off to infinity, and the minimum, they go off to minus infinity. So these are unbounded. These are the 4 types of sets, and even though I haven't given you a precise definition of countable and uncountable, I hope you can feel the difference between them. We can talk about sets in relation to other sets, and one of the ways we can do that is by talking about subsets. So here's a definition. A set H is a subset of another set S if all the elements of H are also elements of S. Here are some examples. So if, again, we use our standard example, if A is the set of all countries in the United Kingdom, let B be the set of all countries in the landmass of Great Britain. So A contains England, Northern Ireland, Scotland and Wales, but B only contains England, Scotland and Wales. Then all the elements of B are also in A, and so B is a subset of A. You can think of B as a smaller version of A. That doesn't mean that B is inside A, because the things that are inside A are the countries themselves, and they are also inside B. B is a subset of A. And we use this symbol for subset. Here are 7 sets, and I want to ask which of these are subsets of the other. And look, all these sets are defined either by listing out the elements or by defining things. Right? So which of these are subsets of the other? Which of these contain elements which are also in other sets? So all the elements of A is contained in B. -2, -6 and 7 are in both A and B. So A is a subset of B. All the elements of A are also negative numbers. So all the elements of A are also in C. A is a subset of C. Looking a bit further down now, D contains all odd numbers. So all the elements of D are in E. D is a subset of E. And let's think of the bottom two. So E is a set of all the odd numbers. An odd number is not divisible by 2. So all the elements of E are also in F. E is a subset of F. Could B contain more elements than A or not? Now in 3 of these, so B does contain more elements than A. C is all the negative numbers. Now A is only some of those negative numbers, so C contains more elements than A. And E is a set of odd numbers, so E contains 3, for example. So E contains more elements than D. So for these 3, the right-hand side contains more elements than the left-hand side. And so we call these proper subsets. A is a proper subset of B. A is a proper subset of C. D is a proper subset of E. And analogous to the less than symbol and the less than or equal to symbol, the subset symbol looks like a proper subset or equal to symbol. But we don't call it that, but that's kind of what it means. They could be equal or not. The final example I've got here, so E being a subset of F. Now, all odd numbers are not divisible by 2, but all numbers that are not divisible by 2 are also odd numbers. So E and F actually contain the same elements. So we can actually say here E is equal to F. And that's what we mean by equality of sets, that they contain the same elements. But E being a subset of F is also true, but E is not a proper subset of F. E is equal to F. They're actually the same set. That's what equality means. You can imagine these two just being 2 names for the same thing. E and F are just 2 names pointing at the same thing. The last thing we're going to look at is it possible to have a set with no elements at all in it? And the answer is yes. A set without any elements in it is a very common thing that happens in maths. It's so common, in fact, we have this symbol for it, this O with a slash through it, and we have a name for it. We call it the empty set. Why is it the empty set? Well, like I just said, any sets that contain the same elements are the same set. So all the sets without any elements are all the same set. So there's only one of them. That's why we call it the empty set. And it's empty because there's no elements. The empty set, so obviously it's a subset of itself. All sets are a subset of itself because they contain the same elements as itself. But the empty set is also a subset of every other set. Now, if you think about our running example, A is the set of the countries of the United Kingdom. The empty set is a subset of that because all the elements in the empty set are in the set of countries of the United Kingdom. There's just none of them. So the empty set, there's only one of them, and it's a subset of every other set.